we were looking at last time. This section deals with three processes: areas under a graph. Next, we're going to talk about distance traveled by moving object and the average value of a function. Those are the ones that we're going to be looking at. This is all on the sheet that you have. So we've talked about the area already, and breaking it up. What we haven't talked about is the error factor of it, because we can estimate the error with the same graph we did last time. Now here's x1, x2, x3, x4, and that's x5. All right. So what we have here is, you see it. This is the right. It's the right side or right end. And this is the left side or the left end analysis. Because on the right-hand side of that's of your rectangle. So no matter how wide we make our rectangles, or delta x, the right side, the inscribed areas, will always be less than, eventually you'll get to equal to the right side. So the value here will be always less than the value here. And then we mitigated some of our error factors. Well, the way you would find the error, or acceptable error, takes a larger minus a smaller, and then you'll see what, because we know somewhere within this bound, somewhere between this bound, is the true area. But it all depends now on the error factor. The farther these are apart, the more iffy is the area. So as our delta x's go to 0, this becomes smaller, so eventually our error goes to 0.
Delta x, is that the difference?
The width. Yeah, it's the distance between x1 and x2. It's a delta x is always that. It's always x2 minus x1. So this is what we didn't talk about this last time, but the smaller the error, the closer we get to our actual area. I'll put the area here, because we know it has to be between these areas. As delta x gets smaller, these numbers get closer and closer and closer. Eventually we'll get to as delta x goes to 0, we get the infinitely small areas, and eventually these are all three will be equal.
And the actual area
Is 8, right?
But we don't know.
We don't know that, yeah. So, but we do have another method that we can come up to, where we call the midpoint method. This is called the midpoint method. Because here what you do is find the average of the distance, average distance between the midpoint between each of these intervals. And then that is the point so your point on the graph is the midpoint between the intervals. So this one goes up to here. So the intervals are still the same width. It's just that you notice from the point on the graph, that's when we make a horizontal line. So from this one, we got the width, out the width, out the width. And this one, we always go with the endpoints. The left endpoint is this one. The right endpoint is this one of the interval. This one we take in the middle. So we have a little bit of overlapping and a little bit of underlapping.
So it kind of averages it out.
Yeah, it's just the average method. This way is a lot more accurate because it takes in consideration those two error factors.
You're taking the sum of the averages.
Right. And it's still not going to be precise because of the error factor itself, how the curve bends.
Right.
So there's this area here of this one, of this under part, is not the same as this area. So it's not an even wash.
So the differences between the top and bottom are like
Right.
consistent.
Not consistent. So if they're not equal, if they were equal, it'd be much better. Which eventually something will just the more erratic the equation, the function, we have something called the norm. The norm is once we partition these things, it's the largest delta x.
The partitions or the interval
Is these intervals, yeah. And this is this one, this one, this one, this one. Those are all the partitions. So from this is P1, P2, P3, P4, P5.
and they're all part of the same partition.
Right. Well, yeah, all the partitions, because the sum of all the partitions equals the whole graph.
Okay.
So we're just taking it. In this case, we partitioned it into 5 different rectangles. But it won't always be so nice because this graph is pretty much smooth. If it was more erratic, then our delta x's would be varying sizes. Kind of like a topo map, topology map, where you see all those little lines. The more steep, the closer you are together. The less steep, the farther out apart. Same thing with these things.
Oh, okay.
The more steep it is, you want because it'll cover the whole thing. Now, so that's with area. What we left off at was the next part we talk about is distance traveled. We could do exactly the same thing that we did with the area under a curve, but instead of a curve, we're looking at the distance traveled and we're separating it into different velocities and different time periods. So let's look at this first example. The velocity function of a projectile fired straight into the air, straight up, is f of t. So our function is f of t 160 minus 9.8 meters per second squared. Where 160 is the initial velocity, 9.8 is the force of gravity pulling back down. Using the summation techniques just described, Estimate how far the projectile rises above during the first 3 seconds. So a second 1, a second 2, a second 3.
So we know the first interval.
Well, yeah, because now it's gonna be more difficult because with the intervals, with delta x's, well, all our delta t's. Because okay, first off, whenever you have time, that is always the x-axis. Time is always the x-axis. So we'll be now looking at delta t's. How close do the sums come to the exact value of 435.9 meters? 435.9 meters. So what we're going to look at is how close is, after we add up all 3 pieces, do we get to it? Okay, so explore the results for different numbers of subintervals. As we said with the areas, the more subintervals you have, the more accurate you become. So notice the fx is decreasing, so choosing the left endpoints give us the upper sum. Okay. What does it mean by upper sum and lower sum? This is the upper sum because it's on the upper part of the graph. This is the lower sum because it's the lower part of the graph. So that's what we're looking at here. Choosing, that's the left endpoints. As I said, the left endpoints give us the upper sum because it's the upper, that's the outer one. And the right endpoints give us the lower sum. So here we have the upper sum and the lower sum. That's what it's saying. The areas between these will be somewhere between those two. And that's the area of the error. Okay, so part A, the three subintervals of length L with F evaluated at the left endpoints give an upper sum. Okay. Because remember, it's going up. And there's not really a left or right because what we're looking at here is if it's shooting straight up. Here's T1. Here's T2. Here's T3. But they just decided to put it sideways instead. So here's our time intervals. And then between each of these, we have our delta T. T2 minus T1. So what's the formula for distance? Rate times time. Yeah. This is algebra. No, it's a motion problem. Yeah, I should have prefaced it. You're right. You're right. It would have been the square root of x2 minus x1. Yes. No, but this is a motion problem. Distance is rate times time. This is rate times time for each interval. So in our first interval, the function f, remember our function f is 160 minus 9.8 meters per second squared. So that's the first interval, the second interval, the third interval. The rate is the function times delta t. That's the distance. So what we have to do here for each one of these time differences, these time intervals, because we know our delta t is 1, because we go from 1 second to 2 seconds to 3 seconds. The difference is 1 second. So if we look at this thing, our first time, we start off at time 0. At the first interval, that's 1 second. Then it's 2 seconds. Then it would go on every second after that. So This is what the problem is, a lot of people don't see. Whenever you either have a time, if you don't have a time zero, then your time one will be your initial value. Right. You know, if it doesn't say T0 is your initial, then we say our first time value is at 0. Our second time value is at 1. Our third time value. Because we're going to be looking for the average rate of all this anyway. So at time 0, what's our displacement? What's our distance? 0, because we're on the ground. So that's what we're saying here. That's what it says here. So the function at 0 is 160 minus 9.8 times 0, because that's our initial time function. So this one at the initial value is 0. Then in our next interval, we have at 1. This is at T1, T2, T1. T1 was 0, T2 is 1. So we have 160 minus 9.8 times 1. Times our delta T. Well, the reason I didn't go any further because it became 0 anyway. Oh, no, that's right, wrong. This is only with that. The time factor. This is a constant. So this is going to be 160.
Okay.
Yeah. Now at this one, it's going to be 160 minus 9.8, which is 150.2. And then at our third time interval, at FT3, the reason it's times T is because it's meters per second squared. So it all depends on how many seconds that tells us this. So T1, T2, T3. T2 is at time 1. And T3 is at F of 2. $160 minus 19.6. $140.4. Okay, those are just the F functions. These are the vertical values. T1, T2, T3. F of T1, F of T2, and F of T3. Remember, our displacement is F of T delta T. And delta t for each of these is the same. It's always 1. So we have 160 times 1 plus 150.2 times 1 plus 140.4 times 1. And if we add those together, 2, 3, 4,
Six.
for what?
450.6.
So that's how far our displacement was.
So that's just, you're just using the idea of the delta T. And these are your, like, this is basically, right? You're finding the, like, accumulation of the,
Just actually the opposite. Integration, we find the area underneath it. We're going forward instead of backwards.
okay.
But if we were looking for that, we all this is looking for is linear movement or physical movement in a vertical sense. So after 2 seconds, we've moved 450.6 meters. That's what it's telling us. Because at the initial at 0 second, at 1 second, at 2 seconds. After 2 seconds, our total movement, each one of these are the movements in that interval. From 0 to 1, we move 160 feet, meters. Then from 1 to 2, we move 152 feet. And then from 2 to 3, we move that in our intervals.
Those are sub intervals.
Right. The partitions would be in our delta T's, T1, T2, T3. So we're cutting.
Each delta T is its own partition?
Yes.
Okay.
In this realm, it would be the same, right? So now what this is telling us also is if you can see our distance is decreasing because of our increase in the gravitational acceleration as opposed to the decreasing of the vertical acceleration. Okay, so that was the first one. That's really good. So now for the 3 subintervals, so part B, for the 3 subintervals of length L, we start off at T1, which is 0, T2, which is at 1, yeah. This one's going to start off at 0, because we're looking at from 0 to 1, 1 to 2, 2 to 3, 1 interval. Yeah, so this is 0. This is our first time period, so it finishes here, here, and here. But now we're looking at the subintervals, the 3 subintervals. So the distance here, remember, it's still rate times time. So it's still going to be the function times delta t. Now, how does this one change? Remember we had the left and right, the upper and lower sums? This one was the lower sum. Because here, I'm put it horizontally. T1 was 0, T2 is 1, T3 is 2. Now, the second part, we're going to look at the upper sums.
So we'll basically we're adding.
Yeah, so here, instead of starting at 0, we now go to the right end. That's our first time period. So The lower is the left end. We start from the left end of the intervals. And the upper sum, we start from the right end. Now, how is this going to change our values? Delta t is still 1 because it's the difference of each interval. F of t is still 160 minus 9.8 t times delta t. And delta t is 1. So this is at t1, t2, t3. Because all the delta t's are 1, so I'm not going to put those there. Because now we look at what are the values of t1, t2, t3.
T1 is 1. So 160 minus 9.8 is 150.2. 9.8 times 2 is 19.6. So that's 140.4. 9.8 times 3 is 29.4. So 160 minus 29.4 is 130.6. This makes it 1, 2, 3, 421.2. So that's just only with 3 subintervals. Let's go with 6. Part C says with 6 subintervals. And remember, we're still looking at the question still said for the first 3 seconds. So we're using half seconds.
Right. So now our delta t will be half. Now that good. Okay, it doesn't want us to do all 3 of them again. So let's just look at those. Let's look at the left side. Your left end. We want 6 intervals. So this is T1, this is T2, T3, T4, T5, T6. Zero, half, 1, 3 over 2, 2, 5 over 2, 3. You see, okay, let me write the formula the way it would look like if we were doing this. Since we're looking at I equals 1 to 6 subintervals. This is how we use the summation symbol. Because what does this mean? It means 160 minus 9.8 T1 delta T plus 160 minus 0.8 times T sub 2 times delta T. 160 minus 9.8 T3 delta T 160 minus 9.8 T4 delta T 160 minus 9.8 T5 delta T So what is delta T? One, because from 0 to 1/2 is 1/2. And for the first one, T1, since we're doing on the left side, T1 is 0 times 1/2. T2 is 1/2 times 1/2. T3 is 1 times 1/2. T4 is 3/2 times 1/2. Half. So here's all I'm doing is putting T1, T2, T3, and I'm just substituting those in there. So this one, the first one is 160 times 1/2. 160 4.9 times 1/2. 160 minus 9.8 times 1/2. 160 9 14.2 times 1/2. I'm adding 4.4, 4.9, 4.9. This is 7. And the next one is 160 minus 19.6. And the last one 1, 2, 3, 4, 5, 6. So if we add up all these, what do you get?
I got 443.25.
Right. That's, yeah, 443.25. That's with the left end.
On the right.
On the right side, so this is the left side. The right side is 428.55. So we know the true answer has to be between those two. So now, once we find the actual value itself, we can find the error magnitude.
That's gonna be the left minus.
No, that would be just the error factor itself. This is the error magnitude. How much is the error? If you look at this, this is the absolute value of the true value minus the approximate or what we calculated. So if we know the true value, we can find the error magnitude. Because what this is looking for is how bad are we really off? The other error between the highest and lowest shows us how far we are, what our answer could be between there. And every time we increase the number of delta x's, the actual error should be getting smaller and smaller and smaller. So what we're looking for with the error between the highest and lowest is we want them to be small as possible. Once we get that, then we get a true value. Then we can now compare the true value to these other values, to the left end and the right end. That's what this error magnitude is all about. And
so we know that our true value is between those two. So do we
yes,
use like an inequality to describe the?
Well, that's what it is. It's always the left right end, because left end is always, I mean, the right end minus is going to be less than the left end. And so because of that, it's always going to be inequality. It'll be less than equal to. Like I said originally in the first page. What was that? Oh, here, it's this. The lower value is going to be less than equal to the area, the true value. Because now as these get smaller, as these get closer, oh, they found the kid. These, no, actually, I get all those Amber Alerts.
Oh,
Yeah, it's just scary to see how many kids are being kidnapped.
it is. I had turned mine off just because I was like,
Every 5 minutes you get one. So yeah, so this is what's that? Well, what happens is whenever a kid disappears, and this one here, they think it was his father who kidnapped him. They don't know what's going to happen to him. Because what happens is they become targets. They take them to Mexico and get sold in the sex market. Or the father could be in debt by the cartel, and that's his get out of jail free card.
Yeah.
Give us your kid, and he has no remorse. He kidnaps his own kid.
Yeah.
So
I think you can see that that it is not.
So this is the error magnitude, the difference from the true value to what our calculated value, whether it's high or low end. That's why it's absolute value. But since the true value is going to be in the middle, If we do the true value minus the low, it'll be a positive number. If we do the true value minus the higher end, it'll be a negative value. And then so we have the absolute value to find the distance. And the error percent is just that. It's how far of our error magnitude, the part, how far is it from the total, which is the true value. Again, that ratio, the smaller we can get it, the better. All right, the next section of this next topic of this first section is the displacement versus the distance traveled. Remember what displacement was? We talked about in the movement. It's how far something moved from one point to another. So it's the position 1, position 2. Displacement is the difference. So in here, in this, it's in this object moving. If an object moved with position function s of t moves along a coordinate line without changing direction, we can calculate the total distance. Yeah, from A to B, we can calculate the total difference if it's moving in the same direction without changing anything. That could be also distance equals rate times time. But our rate this time, since we're dealing with movement along a time interval, that's the velocity. The velocity is the displacement of the position. S2 minus S1 over T pretty much. I mean, this is very, very rough because it's giving us how far it traveled. But remember what defined velocity? How do you define velocity? Of displacement, right? So what we're going to have here, instead of our rate, it's going to be our velocity. Because distance traveled is just that. How far does something travel? It doesn't take into consideration any changes of velocity or anything. Now with displacement, we can take in consideration change in velocity. So our displacement is going to be this formula that I actually put earlier, right? Summation of the absolute value of the velocity of Ti that's what's going to be. And we have example 2 there in a second. Because all of this means the velocity at time interval 1 plus the velocity at time interval 2 the velocity at time interval n. That's what it's saying. Because we're going from 1 to n. So let's look at example 2. In example 4 in section 3, we analyze the motion of a heavy rock blown straight up by dynamite. I remember that one. In that example, we found the velocity of the rock at time t was 160 minus 32 feet per second. Which is almost exactly the same as our previous example. 9.8 meters is 32 feet. So the rock was blown 256 feet above the ground 2 seconds after the explosion. 256 feet in 2 seconds. That's the height. And reached a maximum height of 400 feet in 5 seconds. And then fell back down a distance of 144 feet to reach the height of 256 feet again. Down to 256 feet in 8 seconds. The total distance traveled is the maximum all the way up. The distance from 400 to 256. So it traveled a total distance of 544 feet. Because remember, it blew up, it launched, it came back down. The maximum height it reached was at 400. And after 2 seconds, it reached 256 feet. This is time. But then again, on the way down, that should be the perfect parabola. At 8 seconds, it was also at 256. So from here all the way to here was a total of 544 feet. After 8 seconds. Okay, so that's the actual distance. Let's use our formulas. Let's use our formula to figure this out. This is called the estimation. So how many time intervals does it want? Okay. So from t equals 0 at 0 to t equals at 8 seconds, we could do it in 8 intervals, or we could do it in 16 intervals. If we do it in 8 intervals, what's our delta t? 1. If we do it in 16, our delta t is? So you see now what, and it all depends now. You see the length, this is why computers come in handy. Are we going to do left side or right side? Are we going to do it the low end or upper, lower sum or upper sum? So we have to pick which one. If not, then we'll do both of them and find the error and see how far we are off from the true value of the distance.
So can we pick one, or do we need to?
Let's pick one, yeah, because in reality, we have to find both of them. And then we'd also want to compare the midpoint rule, which is supposedly more, and we see how accurate that really is.
So we're comparing these different models
to see which one we want to use, right? I mean, if you're going to use the left end, right end, then you know you're within a bound. And as we increase the number of ends, 160, then we have much more accurate, because we'll get closer and closer and closer to our total distance of 544 feet. Because that's what we're looking at. Or we can even look at if n equals 4 intervals, our delta t would be 2.
So we already know the total distance.
Because we did the calculus part of it.
This is just the
estimating. This is if you didn't know the true value. But since we knew the true value because of this, and we knew that after 8 seconds, it was back to where it began. And so how far did it travel? From 0, it went up to 400 feet, and it traveled back down to here. Well, how far did it get here? After 8 seconds. So it's 400 feet this way, and then from 400 down to 256, it was 144. So we know how much the total distance was we traveled. So to find, now I'm going to use the 4. I'm going to use n equals 4. We're going to do 4 intervals, because we have to plug in our values of 160 minus 32 times 0 times 2, 160 minus 32 times 1 times 2, 160 32 times 2 times 2, and then our last one is 160 minus 32 times 3 times 2. Because here we're looking at the lower end. We're going at 0, 2, 4, 6, 8. And the lower end of each of these intervals is at 0, 2, 4, and 6. No, I'm sorry. This is not 1. This is going to be 2. This one's going to be 4, and this one's going to be 6, because I cut mine into 4 pieces. Because we have to look at the lower end of each of these intervals. That's what the time value is going to be.
lower interval.
because we're doing n equals 4. So we're doing 2-second intervals, and we're doing also left end. So that we're doing lower sum. We start with 0. And then the next interval starts at 2 to 4, so we start at 2. Then from 4 to 6, and 6 to 8. Those are all ours.
And when we do the right interval, we start at 2.
2, 4, 6, and 8.
Okay.
Because we only want 4 intervals.
So it's essentially when you're moving from the left to the right interval, you're just adding 1 delta. Is that right?
You still have the same number. N tells you how many delta t's you're gonna have. Oh, yes. Either the t sub 1 is here or the t1 is here.
And then that's because when you look at the graph, the way that you're cutting up your intervals in relationship to the curve.
Right, and that's what we'll enter delta t t sub 0 later on. Their times are going to be at the beginning 0, 2, 4, 6, 8. Now I define which one's t1, which is t2. If it's left end, this is t1. If it's right end, this is t1. So I look at my first interval. That tells me my t1, and then from there I build up from there. -60 minus 32 times 64. 160 minus, that's 128. $160 minus 1. If we do all those, we got what? Yeah, and we figured it's going to be lower than 544 because it's the lower end. It's very far difference too, because we only took 4 intervals.
So it's less work for a person, I guess. For a computer, it doesn't really matter. But
yeah, it's to use wider intervals.
So,
I'm gonna use an interval of 8.
Yeah, maybe the computer wants to.
Yeah, knock yourself out. But yeah.
I can take this more.
Yeah, in the computer, all you do, like Excel even, you just type in this formula, and this is your intervals. That's your x you're importing, and that's always going to stay constant. Or you can even add up everything and at the very end multiply by 2 instead of doing each one separately. That's a common factor is 2, so we can factor that out and do the summation of 160 minus 32 I. That's the summation. So it's going from 1 to 4.
And you could like set this up in Python too.
Very easily, yeah. Because it'd just be an iterative process. Repeat this loop from 1 to 4 times, or 1 to n times.
So when you could just use like a for loop and then use the range. Or
You do an if statements. If the counter isn't finished yet, then
okay.
or you can even say, if you wanted to, you could say, because you know what the true value is, you can do the for loop until the summation is this, and then they'll see how many iterations it takes, and that's how far you are.
Okay, and I can actually tell you how many intervals you did with that.
You go on infinitely, but you have to give it some margin of error. So how far is acceptable? And then again, it's the degree of accuracy of the numbers themselves. Is how far do you want to keep it going?
This is a lot like statistics, really.
Very much so, yeah. It's again, statistics was built well after math.
Right.
And actually, now you understand what I'm talking about. Is if somebody just has a master's of math education, they didn't go through all this other stuff of applications and engineering.
Understanding recursion and
Yeah, if you ask that same question to somebody else, they'll just give you the textbook answer. And it's much more than that.
Whereas, like, because a computer scientist is basically a mathematician. And
yeah, it's mathematician using computers as a calculator.
Yeah, right. So I guess if you had math education, you probably wouldn't know a lot about computer science, which is
Very little, you know, very, very little. That's why they use for everything to calculators.
yeah, and then they don't know how to use an Excel or how to, you know.
Oh, they may know how to do Excel. It's just that, but they wouldn't know how to do Python or C or Fortran. Fortran was built for this. This is what NASA Fortran is what and NASA used to send the first rocket to space. Because it stands for formula translation, and that's what it's used for.
Is, is Fortran even really used that much for the day?
It is by C.
See, okay. That's like the predecessor.
Yeah, the Fortran is yeah, exactly. But the compiler that C uses is the Fortran compiler.
Oh, okay.
So because it has Fortran compiler has all the value of the functions.
Right.
Nothing else really does.
So is a compiled language, because Python is an interpreted.
Interpreted language. There's another compiled is we have a program that takes each line and analyzes it. It's compiled to the overall thing. Interpreted is another thing. It's now saying, is the logic flow there? But then you always have to check your values there. If you even have a typographical error in Fortran or C or any of those compile languages, it'll give you anything related to that. It'll give you 1,000 explosions.
So,
errors.
so would Python probably be preferred for mathematicians and like
It's used a lot more. Yeah, it's used a lot more in mathematics and statistics than anything else.
since it's the language. I mean, it's a lot easier to learn. Two, it's also you have more applications, I guess. You've got more library. I know you have more libraries like NumPy. And stuff.
Exactly, and because of those libraries, you have the infinity of which you can use it for.
You don't even have to write the code half the time. Find a library.
Right. And yeah, and all those subroutines are now already integrated in there. So
yeah, they know about the library.
all right, so the last section we have here is the average values of non-negative continuous functions. Average value of a non-negative continuous function. Okay, here we have to look at why did they say, okay, we can guess what average value is. We know what an average is. Non-negative and continuous. Why are those important? It's either increasing or decreasing. All we know there is we won't have any situations like this because this and this will wash itself out. So if it's always non-negative, then we can find those areas and sum them up. So we're always automatically going to be looking for a summation of something. It's got to be continuous because if you have a jump discontinuity or discontinuity somewhere, then we have to now, instead of going from A to B, we're going from A to C, then C to B. This right side won't work, so it has left side. Now different values. So is it approaching? So yeah, it's got to be continuous. If you have any type of discontinuities, it won't give you too much of an answer. Let's go ahead and look at what this example means. Example 3. Estimate the average value of the function of f of x equals sine x on the interval 0 to pi. Again, here we go again. is we have to look at what is the number of intervals you want to have. The fewer the number, the more error you're going to have. So let's say we're going to deal with 8 intervals. We're going from 0 to pi. So this first one is pi over 8. Next one is 2 pi over 8, which is pi over 4. 3 pi over 8. Next one is 4 pi, which is pi over 2. 5 pi over 8. 6 pi over 8 is 3 pi over 4. And 7 pi over 8. And 8 pi over 8. And we're looking at the sine function. Sine at 0 is 0. Sine at pi over 2 is 1. And sine at pi. So we're just looking at this semi-dome. We're back to that question. Do we use left end or right end? Upper sum or lower sum? So this one, let's just go here. So we could pick this whole thing here, because if we pick the first one's gone. But now we have a problem. You see the problem? This side now, so we're going to do from this end, well, we now change the bounds. We'll get rid of those. So we're always going to have an overabundance of, so we're picking the high end here. So how do we find the area? The summation, since we did 8, so we have the function times delta x. So, what's that? Yeah, this is y times x, the delta x, the width size, yeah. Yeah, because this is, because our function is actually y. F of x is actually y. So we begin. We have sine of our first one, which is pi over 8 times our delta x is pi over 8. That's the width of our intervals. Then we have our next interval. Sine of pi over 4 times pi over 8. Again, we can keep on doing this, or we can factor out the pi over 8 and multiply at the end, whatever you guys want to do. Because each one of these, we're going to have to put a sine 3 pi over 8. Yeah, so if we factor out the pi over 8, then all we have to do is put the sine pi over 8, sine pi over 4, sine 3 pi over 8, and keep on going. Then we go to sine pi over 2. Then sine 5 pi over 8. Then sine 3 pi over 4. 1, 2, 3, 4, 5, 6, 7. Sine 7 pi over 8. 1, 2, 3, 4, 5, 6, 7. Oops, I missed. See the mistake I made? Look at the picture. It's cut into two parts. This one, I use those. I have to use these points here. So that's these first four. 1, 2, 3, 4. Now on the back side, I use the left side. So I have to use pi over 2 again. So I just have to add pi over 2 again. Then I go to pi over 8, 3 pi over 4. So yeah.
Oh, so you have to include that.
Yeah, because this one, I used this point. I used that point. I used that point. I used that point. I made all those left buckets. Now for this right-hand side, to make these right buckets, I got to start with this one. And then this one. So I have to have 8 total intervals. If I didn't, that's the reason I stopped. I only had 7 of them. So I can't use pi itself because it didn't have any box. I used this box. So I have to use these values. This one twice. And this is where calculators come in. Sine pi over 8, sine pi over 4. I mean, some of these we can figure out. Sine pi over 2 is 1. Sine pi over 2 is 1. Pi over 4, that's square root of 2 over 2. Pi 3 over 4 is also square root of 2. Yeah, so we still need decimals for all these. And then multiply by pi over 8. What's your final answer? You can't, because you have to define, if you do that, you have to define what is xi. Xi is, yeah, you have to convert it to degrees. But what we're going to have is I pi over 8. That would have to be your x. So you would have to enter this function if you're going to do the summation. for that part. Which is doable. I mean, you can use a summation. Just use the sine I pi over 8 as your function. And I goes from 1 to 8.
Yeah, we try.
No, well, you can't do that because remember, halfway through it stops. So you have to do it from you have to do this. Right? So you see, because halfway through we changed the bounds. So you'd have to go through 1 through 4, and at 4 through 8, it changes to the other side.
You'd have to use two.
Well, even then, yeah, but then it wouldn't be over 8 anymore. So we have to go through each one of these separately and get decimals. And thanks to my speedy computer on the sheet, it says it's supposed to equal 6.02. And then that's times pi over 8. Okay, remember, this is our estimated area. So you follow that? You get that? Is 6.02? Did you get that somehow? You can't because it changes bounds. So this gives us our estimated area.
Okay.
We have to find the average value. So we take this estimated area, and since our bound is from 0 to pi, our average value is equal to the x sub 2 minus x sub 1 over our estimate. So our x2 minus 1, that's our bound. This is b minus a. Because on the average value, we're looking over the entire area. Since we're going from 0 to pi, this is pi, this is 0. So we have to do to find the average value. We got to take pi and divide it by our estimate value area. That'll give you the average value. Which is approximately 0.753. That's pretty much it for that section. What y'all think?
Not too bad. Yeah.
So
The hardest part is just understanding the the two different bounds.
right, because since we started and we're looking at the upper, so we have the upper sum. We know it's the upper sum because we have wasted area here. So we have to get wasted area over here. If we had the other way, if we had the lower sum, then we have to continue doing the lower sum. Because if you ever have a area that you're looking for that's in a closed curve like that, that changes from one side it's positive, the slope is positive, and one side the slope is negative, and that both halves are equal, then we have to always keep our areas, in this case, it has to be inside. So this one has to be inside. That's what you have to look out for. And that's why you can't just plug it in the calculator or computer and just hit enter, because you have to look at the graph as well.
And by doing that, you're getting,
An estimated area, the lower sum area, because this is the lower sum.
yeah, so the lower sum is gonna give you less than the estimation, or, I mean.
Right.
Is gonna give you your estimated, which is less than the
Mm. More than the true. Right. And the upper, because it's the same formula, except what changes is where the dots are. Because this one has its outside. This is on the inside. Remember earlier I said circumscribed as opposed to inscribed? This is inscribed. The lower sum is always looking at the inside. Circumscribed is the outside, like you're going around the world. So that's what this one would be. I'm circumscribing the area. I only want the boxes that are outside the area. You're right. That's the hardest part, is how do you know when do I use it? The graph comes in. Well, you have
I mean, for this one, yeah, but for the, for example.
in average,
Examples.
it usually helps to draw the graph before you start. Because I mean, whenever you do a problem, always look at the graph what you're dealing with. I mean, sometimes it'll give you an x cube function, and it gives you a different a or b. So, but if it's giving you it's like a parabolic, and it says I want it from here to here, and it's equal distance, then you have to look at the graph and know that halfway through it changes for this stuff. When we look at the estimations, this is only estimation. We can find the true area by taking the integrals.
And this is just showing us what came before.
Right.
Like,
Which again, it's giving us same as we did with the epsilon delta proof to find the derivative. That's what this is. I mean, the next section is definite integrals. Then we talk about the fundamental theorem of calculus. Here we are, chapter 5, and we just now got to the fundamental theorem of the class we're studying.
It was all
Leading up to it, right? Exactly. And then so section 2 will deal with the sigma notations, what we did here, sigma notations. So here's your index. You have your beginning point, your end point, and your function. So your first example will be, how would this look? Give me the first 5.
So it would be a plus a 2.
Well, this one here would be this one here. If I expanded it, it would be A1 plus A2 all the way to AN. Because the only thing that changes is my index. Okay, so if I had summation of I, phi equals 1 to 5, the first time through I is 1, then I is 2, I is 3, I is 4, then this is the loop. You keep on repeating this, start off at 1, keep on repeating it until you get to 5. Once you get to 5, you're finished. Then you add them all up. But the reason we in this section, we go through these other ones, because we'll see that these actually come from other functions. So that if it's not possible to find a integral using another method, let's use this. We can use a summation rule and figure this out. And it'll help us to recalculate it. So go ahead and look at this also. And then on Monday, we'll do sections 3 and 4. And then the Monday following, we'll finish the course. Okay.
So, one question. So, how do you differentiate between for example, in the word problem? How do you differentiate the lower and that one?
Well, it'll tell you.
Or-
Well, it should tell you whether it wants an upper sum or a lower sum, what exactly it's looking for. And if it doesn't tell you what it's looking for, then if it's just saying to find the estimate, then just find the estimate, use either one you want to, and go from there. So if it doesn't specifically tell you what you're looking for, then use whatever you want. Yeah. All right, guys, have a great, safe weekend. It's just hard to believe today's Wednesday, and next week is Thanksgiving. Too fast. I mean, time is just literally flying. And after that, after we get back from Thanksgiving, we have 1 week and then Christmas. Then final exams and Christmas. I remember when I was a kid, I used to say, it's taking forever for just Christmas to come, or school's lasting forever.
Yeah.
But my parents go, no, when you get older, it's going to fly by. You won't have enough time for anything.
No, and that's exactly how it is.
That's exactly what's happening. And yeah, and then as older we get, we start seeing a lot of friends start dying off, saying, oh, crap, when's my number? But then he was like the oldest person just died. He was 112 or 114 years old. That would be awesome to see the change. Think of it. If he was 110 years old, 114 years old, he was born just after the first airplane was flown. He saw the evolution of the airplane from 1907 to 1938, 39, when the first jet was built. And then by 1950, there were jets, then we had rockets, we had missiles, we had
Got people throwing the park.
yeah, we watched other people go to other planets. Telephones didn't exist when they were born. Telegraph was the best you can hope for. A letter would take a month just to get to where it's going, and another month to get back. So,
Calculator.
it weren't invented for another 60 years. So,
Yeah, he was elderly when the first calculator was invented.
yeah, he was finished.
He was retired about it. And then he went from that to then seeing